Okay, so remember what we're talking about. We have inner product spaces, right? And we're trying to show that in inner product spaces, you can do a lot of the things that you do in Euclidean spaces, right? And what we were going to do next was the Cauchy-Schwarz Inequality. Okay, Cauchy-Schwarz Inequality. Does anybody remember the Cauchy-Schwarz Inequality in Euclidean space? What does it say? Like, you've got two vectors. You've got two vectors in Rn. Then it says something. There's an inequality involved. No, you're thinking the magnitude of. So I'm going to put in. That's what I meant. That's what you meant. Okay. So the magnitude of the dot product, the absolute value of the dot product, is less than or equal to the product of the magnitudes. That's not what you meant? Okay, good. Yeah, I think you're thinking about the triangle inequality or something.
Oh yeah.
Okay, so not the triangle inequality, but the other useful inequality. Okay, so the absolute value of the dot product, and I should warn you that I sometimes call this the magnitude of the, right? Because the absolute value is basically the magnitude of a number. So the magnitude of the dot product is less than the product of the magnitudes of the vectors. Okay, so that's the Cauchy-Schwarz inequality, and why it's true has to do with, at least in R2 or R3, it has to do with the geometric interpretation of the dot product. Right? What's the geometric interpretation of the dot product? Well, if you take one vector and dot it against another vector, remember, what's the dot product? It is the product of the magnitudes times the cosine, thank you, cosine of the angle between those vectors. Right. If you have the geometric interpretation, well, just take the absolute value of both sides. Take the absolute value of both sides, I can pull these numbers out because they're positive, right? I can pull these numbers out of the absolute value because they're positive already. Okay, and what do I know about the absolute value of the cosine?
0 to 1.
It's between, this is at most 1, right? So we know that this product here is less than or equal to this. Right? So the geometric interpretation of the dot product gives you the Cauchy-Schwarz inequality immediately. You guys see that? Okay. Now, suppose we're in an inner product space and we want to say something about the inner product. Well, there's no geometric interpretation anymore, right? In an inner product space, right, suppose we're on the space of functions and we're talking about the inner product being the integral of one function against the other function. Well, what does it mean? Does that have a geometric interpretation? Do you have an angle between your functions? Well, there's no angle between the functions, right? It doesn't make any sense anymore. So we can't do this, right? This sort of thing doesn't work in the general abstract case. Okay, so we need to do something else for the general thing. So suppose, let me just state it here. Suppose you have these guys in an inner product space. Then the absolute value of the inner product of those two vectors is less than or equal to the product of the magnitudes of those two vectors. So the same thing that was true in Euclidean space holds in an inner product space. There's a second part further, we have equality, right? These things are equal to each other if and only if u and v are linearly dependent. We have equality if and only if they are linearly dependent. Right? One is a multiple of the other. Okay. And so to prove this, we're going to need a couple of tools, okay, a couple of lemmas. Okay, so, right, because we don't have the geometric interpretation anymore. Okay, so let's say that V is a non-zero vector, and let P denote the projection of U onto V. Okay, so again, U and V are in your inner product space V. Then one, U minus P is perpendicular to V. U minus the projection of U onto V is perpendicular to P. Okay, we're going to prove this. Okay, but here's a picture. Like you've got your U, so this is the Euclidean space picture. You've got your U, you've got your V, you've got your projection. Right, you've got your projection of U onto V, and you have U minus that projection. Right? U minus that projection, this guy here, is perpendicular to P. Okay? Okay, so that's the Euclidean space picture. We're in an inner product space, so there is no picture. Okay? There is no picture. Right? This picture doesn't exist. Okay. But you keep it in your head, like, oh yeah, you know, to give you some sense of what it means in Euclidean space. But there really is no picture. Okay. So, big picture. Okay, part two, lemma number 2 is that U equals P if and only if U is some multiple of V. Right? In other words, U and V are linearly dependent. So again, you've got your fake picture, right? The only time, sorry. Okay, in the fake picture, right? The only time U is equal to P, the only time the projection and U are the same guy is if U lies along V to begin with, right? Right? If U lies along V to begin with, then it's equal to its projection onto V, right? Is that clear? Right? You've got U, you've got P. P is the projection, right? P is the projection of U onto V. Right? The only time that's equal is if U actually lies along V to begin with. Yeah, Ethan.
Why are you multiplying by beta for V?
So we're saying that the only time that's going to happen is if U is some multiple of V. Right? If U is some scaling of V. Okay, so these two facts are sort of intuitively obvious in Euclidean space, but we have to prove them. So let's do the proof. Right? Proofs. Number 1, we want to see that U minus the projection is perpendicular to the projection. Right? So remember, the projection is the projection of U onto V. Okay, so we need to check that U minus P against P, if we take the inner product, we get 0. Okay, I'm going to leave that as a I'm going to leave that for you to do. Okay, so just do that as an exercise. Okay, it's just a calculation. It's a calculation. Okay. Number 2, we need to check that. Right. So let me write up what you need to write. So you'd say, well, U minus the projection. Well, that's UV VV times V times the projection UV VV V equals 0. Does this thing equal to 0? And you work it out and see that some things cancel off, and you get something minus the same thing. You get 0. Okay. So let's just assume that. Part 2. We want to see that U is equal to P if and only if U is some multiple of V. Okay, so let's do the forward direction first. Okay, let's do the forward direction first. Okay, suppose U is equal to P. Okay, if U equals P, well, what's P? P is U V V V V. Right? If U equals the projection, and we want to show that U is a multiple of V, right? But we're done already, right? Because look, if U is this, then U is a multiple of V, right? Right? If U is this, the projection is a multiple of V, so we're done, right? Then certainly U equals some multiple of V. Right? Just this is the scaling. This is the number, the scalar. Okay. Going backwards, let's say that U is a multiple of V. Is the projection of U on V equal to U? Is U equal to P? Take a minute and see if you can see that. So look at what P is. Look at what P is, and see that that actually is U. Okay. Take a minute and see if you can write that down. with daylight savings time, this class has turned into the more tired class somehow. Like the other class actually has more energy, and you guys seem more tired than previously. Okay. Talk to each other for 10 seconds and then I'll talk about it. So you say, well, look, then the projection of u onto v is going to be u v over v against v times v.
Value? Oh, okay.
Because u is beta v.
Okay.
Right. The projection of u onto v is going to be u v v v v. Right? And what do you see? Well, you can pull the beta out, right? So you get beta times 1, right? What's left over is 1 times v.
Why doesn't the beta also apply to the v? Why is it only beta from
You pull the number out here, right? So it's like 5 times 5u, right? Is the same thing as 5. Right? If you take the dot product, if you take the scalar product of one guy against another, you can pull the scalar out. Right? This is the linearity of the inner product. Right? So you end up with beta VV over VV times V, but that's beta V. Right? But that's u. Right? And so you see that so P is u. Okay. Ryan, are you okay? Yes? Okay. Okay, great. Okay, so what we have, we've got these two lemmas, right? That show these things that seem obvious in Euclidean space, but they're also true in the inner product space. Okay. Right? That u minus p is perpendicular to p, and that u equals p if and only if u is some multiple of v. Okay. Okay. So now let's do the proof of the Cauchy-Schwarz inequality. So Cauchy-Schwarz. Right? If u and v are in an inner product space, then the absolute value of u, the absolute value of the inner product is controlled by the product of the magnitudes.
We're going to prove the equality.
We're proving the inequality, right? We're proving both. We're going to do. So we're going to do. I'm just writing it again. Okay, so maybe I should just say this. So further we have inequality. Further we have equality. Right? We have equality if and only if u and v are linearly independent. Okay, let's prove it. Okay, so think we want to show that this thing is less than or equal to this thing. That's our goal, right? We want to show this thing is less than or equal to that thing. Okay. Now, that's simply the same thing as showing that this thing squared is less than or equal to that thing squared. Okay, and the reason is that if you have two numbers and they're bigger than or equal to 0, then one guy is bigger than the other if and only if their squares are bigger than 2. The square of one guy is bigger than the square of the other. Yeah.
Why are you only squaring the magnitude of u?
Oh, thanks. Yeah, John.
In the A and B example, is that not taking into consideration what the positive and negative signs? Is that why we square them to get the absolute value?
So, okay, so think about this statement here. If I have two numbers, A and B, and A is bigger than B, and they're both bigger than 0, okay? If A is bigger than B, then A squared is going to be bigger than B squared, right? Here's my x squared function, right? A squared is going to be bigger than B squared, right? Conversely, if I know that A squared is bigger than B squared, I know that A is bigger than B. Okay, as long as these guys are positive, right? Okay, so that's what I'm using here, right? I'm saying, well, I want to show that this is less than or equal to that. I can just as well show that this squared is less than or equal to that squared. Okay, so this statement over here justifies this. So this is a kind of a common trick. Like you want to show that some things are less than or equal to each other, and they're both positive, so you take squares of both sides, and sometimes that's helpful. Okay. Okay. So that's the same thing as this. Right? Just dividing both sides by the magnitude of b squared. Right? Okay. Actually, I'm cheating you a little bit, because how do I know that this is not 0? Right? How do I know that that's not 0? Actually, I should have at the beginning said, notice if b is 0, then the statement is trivial. Right? Right? If v is equal to 0, the Cauchy-Schwarz inequality is saying that 0 is less than or equal to 0. That's true. Right? So I don't have to worry about the case v equals 0. Right? So I can assume, right? So assume v is not 0. Right? Because in the case v equals 0, I'm done already. Okay. Okay, so I want to, so if I want to prove the Cauchy-Schwarz inequality, I need to prove this thing here. Okay, this is our new goal. We're just changing its appearance slightly. Okay? Okay, does anybody recognize this thing here? What's this? The what? The projection. Well, it's not exactly the projection, it's the magnitude squared of the projection. Right? It's the magnitude of the projection squared. It's the scalar projection squared. Right? So this is actually the scalar, this is the magnitude of the projection squared. Right? So again, we changed what we need to show. The Cauchy-Schwarz inequality is basically saying that the size of the projection is smaller than the size of the original vector. Okay, so that's what we want to show, right? Okay, so we want to show that the size of the projection squared is less than or equal to the size of u squared, right? Where p P is the projection of U onto V. Okay. Let's go back to our picture again. Right. Let's go back to our non-existent picture. Right. This guy is P. This guy is U minus P. Okay. So even though this picture doesn't exist, we still had some things that were true, right? That this and this were perpendicular to each other. So recall, by lemma 1, U minus P was perpendicular to U. Right? So we can use the Pythagorean theorem. So by the Pythagorean theorem, by the Pythagorean theorem, what do we know? P squared, magnitude of P squared plus the magnitude of U minus P squared equals the magnitude of U squared. Right? Yeah, Trevor.
Isn't U minus P supposed to be perpendicular to P?
Oh, P. Excuse me. Thank you. Thanks. Great. Yeah, you're not crazy. Thank you. Okay, so the magnitude of P squared plus this thing is equal to the magnitude of U squared, right? Right? What are we trying to show? We're trying to show that the magnitude of P squared is less than or equal to the magnitude of U squared, right? But we're done, right? Because the magnitude of P squared plus something is the magnitude of U squared, equals the magnitude of U squared, right? So this has got to be smaller than that, right? Because this plus something else is that. Right? So this is smaller than equal to that. Right? So you see that. So the magnitude of P squared is definitely less than or equal to the magnitude of U squared. And we have equality if and only if U minus P squared, the magnitude of U minus P squared is 0. Right? In other words, U would have to be equal to P. Right? But by lemma 2, that means that U is U and V. U is a multiple of V. Right? U is a multiple of V. In other words, they are dependent. U is a multiple of V. V. Right? So that's the proof of Cauchy-Schwarz in the inner product case. Okay. You see that it relies on these two geometric properties, that these guys are perpendicular and they are equal if and only if these guys are equal if and only if they're equal. Any questions? This is kind of a cool proof, right? You take the thing you're trying to show, and then you start messing with it, and you change it into something else entirely, right? That's actually easier to understand, right? You're trying to show that the projection the length of the projection is less smaller than the length of the original, which kind of makes sense, and then you see what you need to do to get there. Okay, let's go on. Spent too much time talking about courses at the beginning. Okay, so we do something funny with this. The Cauchy-Schwarz inequality allows us to create angles between vectors. Okay, so we make up angles. Okay, their angles don't exist, from the beginning, but we're going to make up angles. Okay, so now we say given two vectors in an inner product space, we define the angle between u and v to be the arc cosine of u and v's inner product over the product of their magnitudes.
That's just equivalent to the top product.
We sort of base it on what happens in Euclidean space. Okay, in Euclidean space, it turns out that the dot product is the product of these things times the cosine of the angle. Right? So in Euclidean space, this is true, right? Because you have u dot v. In Euclidean space, you have u dot v is magnitude of u, magnitude of v, cosine of the angle, right? So that's true, but in your inner product space, there is no angle to begin with, right? So we make up an angle in such a way that this relation holds, right? So in that case, then, by construction, u v equals the product of the magnitudes as the cosine of the angle, right? Because you made it, that's how you define the angle, right? You define the angle so that this is true. Okay, so it's weird, yeah. So there's no angle a priori, but you make up the angle. You make up the angle so that this geometric relation is true, is trivially true. Okay, you're cheating, right? Okay, but you see that we needed this thing to be smaller than 1 in order to take the arc cosine of it. We needed this thing in absolute value to be smaller than 1 so that we could use the arc cosine. And that's why we need the Cauchy-Schwarz inequality. Right? Cauchy-Schwarz inequality says that this thing will be less than or equal to 1 in absolute value. Right? It makes, so that the arc cosine is defined. Otherwise, we don't know if this is defined or not. That's the last bit of the introduction to inner products. We introduce another notion now called the norm. Okay. So the norm is basically a generalization of magnitude. Okay. So just like magnitude of vectors. So here's the definition. We want to have some idea of we want to have something like the magnitude. Okay, so be a vector space. So we're not on an inner product space necessarily, just some vector space. Let this thing be a function. Right? Okay, so you have a function going from the vectors to the real numbers. Okay. We call it a norm if the following 3 things happen. The norm of any vector is bigger than or equal to 0. And the norm equals 0 if and only if the vector is 0. The norm of a scaled vector is just the norm of the vector times the absolute value of the scalar. Right? And triangle inequality, the norm of a sum is less than or equal to the sum of the norms. So these are all things that magnitude does, right? If you're back in Euclidean space, you think about magnitude. Magnitude has all these properties, right? And so we're saying we'd like something for our abstract vector space that has these properties, and if it does, we call it a norm. Okay. And we call V a normed vector space. Normed vector space. If all of these three things are true. Let me just quickly give you some examples. First example is in Rn. Your standard norm, right? The summation of the components squared, everything to the 1/2, right? That's a norm. Okay, so that's just your normal magnitude. Okay, let's call that example 0. Okay. Example 1 is what's called the little LP norm. Okay, the little LP norm, which is you take the sum of those magnitudes to the pth power and raise the whole thing to the 1/pth power. Okay, so instead of 2, you use some other number p, where p is bigger than 1, bigger than or equal to 1. Okay. Example number 2. Something called the little L infinity norm. It's defined as the max of the absolute values of the components. Okay, so you take like if your vector is, say, -1, -5, 5, 6, say, then the L infinity norm of that would be 6. You just take the absolute value of each component and take the greatest value you get. If V is an inner product space, then you can define a norm as the square root of the vector against itself, inner product.
So for a particular vector space, you can have like different definitions for what a norm is.
That's right. Yeah, so you've got your vector space Rn, but you've got different ways of measuring the size of a vector. Sorry to keep you up. You've got different ways of measuring the size of a vector. And remember, if you define distance, right? Distance between two vectors, you define as the norm of the difference, right? So you can also define different ways of measuring distance. Okay. Like what does it mean for one vector to be close to another? Well, it depends on what your norm is. Okay. So let me just do one kind of cute thing. In L2, right, what does the unit disk look like? Suppose you're using the L2, your standard norm. What's the unit disk look like? Everything that's distance 1 from the origin, or size 1 or smaller. Well, it's a circle, right? Okay. What if we use the different norms? For example, the L infinity norm. What are the guys who are distance 1 or size 1? What vectors are size 1 or less?
Unit vectors.
In R2, right? So we're in R2 here. We're in R2. We've got some vector x, y, and we take its L infinity norm. Its L infinity norm is the max of absolute value of x and the absolute value of y. Right? So what guys would, for what vectors would that be less than or equal to 1? Well, this would have to be less than or equal to 1, and that would have to be less than or equal to 1. So what does the unit disk look like for the L infinity norm? Anybody see it? Not a circle.
Radius.
Sorry? Backed off. Okay, let me ask this. Is this point 1, 1?
No.
Is this point 1, 1 in the unit circle? Is the max of 1 and 1 less than or equal to 1? Yes. This point is in the circle. It's a square. This is the unit disk, right? This is the unit ball with respect to the infinity norm. The unit ball with respect to the L1 norm. Is this fun? I don't know if this is fun. I'm going to just say one more thing. What about you want the L1 norm? Remember, the L1 norm is that the sum of the absolute values has to be less than or equal to 1. What does that look like? The L1, what's the L1 unit ball look like?
Is it the square that's like inside the circle? Like it's like
Exactly.
diagonal.
Great. It's this. That's the L1. That's the L1 ball. Okay. And as P gets bigger, the unit disks get fatter and fatter and eventually tend towards the square. As P tends towards infinity, the unit balls will spread out towards the square. Okay, sorry to keep you over. That's it.
On the second norm,
Yes.
summation at I equals to 1 or?
Oh, it should be I equals 1. Sorry.
All right.